Hi, hello everyone, welcome to the channel. So in this video we want to look at the properties of the Earth's surface that can be detected by remote sensing instrumentation. When we examined those properties, we will understand why a certain wavebands have been chosen in the designs of sensors commonly used in the civilian remote sensing missions. So first, remember the most remote sensing missions records the images of Earth's surface using a reflected sunlight. Just as you and I see the Earth as a result of reflected sunlight. In remote sensing through the wavelengths outside the range of human vision can also be used for imaging, but let's just concentrate on the reflected sunlight. If the Earth's surface wasn't an ideal reflector, such as a sheet of white material, then all the wavelengths could be reflected equally. The real Earth surface materials, however, are not an ideal reflectors. They selectively absorb sunlight at different wavelengths, giving the appearance of the color in the visible range. For example, the green vegetation appears to us as a green because in the visible range of wavelength, there is a strong absorption of incident blue and the red radiation from the sun, but less absorption of green sunlight. As a result, there is a more green energy reflected from most plants matter, so that we see grass, trees and other green vegetative matter as green depending on their pigmentations. Some plants are differently colored. For example, the plants which appears red strongly absorbs the incident blue and green radiation, but reflects a significant portion of the incident red radiation from the sun. To develop a better idea of what a satellite sensors detects, including in the range of wavelengths beyond the human visions, we will now examine in a little details the reflectance properties of the Earth's surface material as a function of wavelength. So this image shows three simple fundamental Earth cover types of vegetation, soil and water. Reflects the incident sunlight across just the optical range of wavelengths. So here in the vertical axis is calibrated in percentage of percentage reflectance. So the amount of sunlight reflected is expressed as a reflectance. And also take in note also that the range of visible wavelengths are shown at. So the visible wavelengths are given here. So and also I should note that the range of visible wavelength here, it's small compared with the full range of optical wavelengths. And it is important to note that the amount of green energy reflected by the green vegetation is really quite small. Nevertheless, it is larger than blue and red reflections. So you can able to view here. So the vegetation has a higher reflectance, that is, a green vegetation has a higher reflectance in this portion of wavelengths compared to the soil and red, which has a very low reflectance compared to the vegetation. So the higher reflectance of vegetation, which indicates that we are seeing most vegetation as a green, even that the energy levels are quite small. So in the visible region, this is a visible region, so you can able to observe here. So in the visible portion of the electromagnetic spectrum here, so you can able to observe the vegetation has a higher reflectance compared to the water. And when you compare to with that of soil, the soil has a higher reflectance in the visible portion of the spectrum, the visible portion of the spectrum here. So in the visible range, the soil has a higher reflectance followed by the water, and next we have our vegetation reflectance in the visible portion of the spectrum. So by contrast, in the near infrared region, so this is a near infrared region, the vegetation reflects about 30% or more of the incident light, that is incident sunlight. If we were able to see in the near infrared region, the vegetation could look much broader than it does in the optical range. So as we move to the longer wavelengths still, we see that vegetation reflectance curve drop away. So it contains the two large absorption dips. So you can able to observe in this portion of electromagnetic spectrum. So vegetation has a two significant absorption dips. So you can able to observe the dips here. that is resulting from the water content of the vegetative matter. The depending upon the moisture content of the vegetation, those dips can be very deep or quite shallow. If the vegetation is moisture stress, the dips will be shallow to non-existent. The most remote sensing instrumentation tends to avoid the imaging in those regions. The water absorption dips also occurs for soil. All through in this real example, the soil is quite dry, so that the dips are very shallow. So you can able to observe from here the soil has a reflectance, high reflectance in this region, and also there is a shallow dip in this region, indicating that the moisture contents are low, which is indicated in this region. So you can also observe dips in this region, the absorption dips. The soil with high moisture content shows the dips comparable to those in this case to the vegetative curve here. So you can able to visualize the soil with high moisture content, so it shows a significant absorption dips compared so kind of like this vegetation curve here. You can able to see that. So soil with a higher moisture content, if the soil has a very high moisture content, so there will be a significant dip here, like the vegetation curve here. The other interesting property about soil is the reflectance curve rises steadily with increasing wavelength in the visible and infrared ranges. As a result, the visible color of the soil is determined mostly by the reflected green and red radiation. Said that the color tends towards reddish yellow. That is particularly the case for the clays and sand. A dark loamy soil will appear blackish because there is a high absorption at all wavelengths. Now the water reflection curve is dark everywhere, so you can able to visualize from this image here. This is the water curve here. You can able to observe it. It is in blue color. You can able to see that it is the water curve reflectance. So the water reflection curve is dark everywhere, showing just a small amount of reflected energy in the blue green range, consistent without an experience of watercolor. So these three curves are typically of what we encounter in remote sensing, but that will vary considerably depending upon the moisture and mineral contents of the soil, the moisture and pigmentation content of the vegetation, and the clarity and the depth of water. If a water contains a lot of sediments, for example, the water curve will be a combination of the reflectance of pure water and that of the suspended soil matter. If the water is shallow, there can be a reflectance from the bottom materials. So when looking at the cover types such as water, the remote sensing specialist needs to be aware that the reflectance is observed can be a mixture of more than one pure material. So in this slide, we show how the wavebands of some common remote sensing satellite instruments are chosen specifically so that they sample the most significant regions of the spectral reflectance curves of the common Earth surface cover types. To consider a simple example, the Landsat ETM takes three measurements in the visible range, roughly corresponding to blue, green and red. So you can able to see here, this is Landsat ETM plus. Another measurement just at the start of the near infrared region, so here, and two broad measurements further out in here in the infrared, avoiding the water absorptions dips. So now the sensors such as the Hyperion, so that is EO1 Hyperion, takes a very large number of samples across the spectrum with sufficiently fine spectral resolution that in principle the full reflectance spectra could be reconstructed for each pixel. Remember, the each pixel is sampled in all of the available light bands, so that the spectral information recorded by any of these sensors is done for every pixel in the image. Whenever you come across a sensor, have a look at the wave bands it operates with. and form an opinion as to its likely applications. If a sensor operates largely in the visible range, it is probably designed for surveillance, mapping, or the urban studies. If it has a wide bands in the infrared, then it is then good for mapping and monitoring the cover types, such as the natural vegetation, crops, and forests. If it operates further out in the infrared range, it is likely to be designed for geological studies as well, since a number of important spectral features of minerals occur in the wavelength up to about 2.5 micrometers. So now we are in the position to introduce some further definitions. If an instrument records up to about 10 wide bands, it is generally referred to as a multispectral sensor. So if it records a very large number of bands, say more than 100, it is often referred to as a hyperspectral sensor. So you can able to observe here the spot HRG here. It represents the multispectral sensor, and EVO1 Hyperion, so it is a hyperspectral sensor. So you can able to visualize the difference between the multispectral and hyperspectral images. So in this stage, it is worthwhile re-examining the other portions of the electromagnetic spectrum, and in particular the region beyond the optical wavelengths. Remember though, we have to be the mindful of the presence of the atmospheric absorption, and can only reliably image over those wavelength which corresponds to the atmospheric window. So as we noted in our previous videos, there are a good atmospheric window in the vicinity of 10 micrometers and in the very broad radio waves regions of the spectrum. So they are identified on this slide here. You can able to see here. One is of radio waves here and the thermal infrared region. Now we need to ask ourselves once again whether those regions are useful for the Earth's surface imaging. Now let's look at the wavelengths in the vicinity of the 10 micrometer first. So this is over 10 micrometer. So now let's move to the next slide. So there is a very famous law called as the Planck's radiation law, which describes how a body, so-called the black body, radiates the energy as a function of wavelength. The radiation emitted is also importantly a function of temperature of the body. The Planck's law is described by an equation that allows us to plot radiation curves as a function of wavelength and temperature. So in this slide, we show 3 examples of the Planck's radiation law in practice. The first example is for the sun here. So you can able to see in the graph here. It is indicated in yellow, whose surface temperature is taken to be 5950 K. The second is for the Earth here. So you can able to see here, which is indicated in green, which has a temperature of approximately 300 K. So third is an object with a temperature of about 1000 K, which is indicated in red color, which roughly corresponds to the burning fire. As seen, they have the maximum radiation outputs at different wavelengths. It is important to note that the vertical scale is a logarithmic, so that the each integer spacing represents a power of 10 or an order of magnitude. And also the sun curve has been scaled down to represent the reduction in radiation because of the distance it has traveled from the sun to the earth. The solar curve has a radiation maximum at a wavelength of about one half of the micrometer, whereas the Earth's maximum emission is at a wavelength of about 10 micrometers. The two curves cross over a little below 5 micrometers, meaning that any observations of the Earth's surface at a wavelengths less than about 4 micrometers are dominated by a reflected sunlight, whereas the emission above about 6 micrometers are dominated by natural emissions from the Earth itself. If we want to measure the natural energy emanating from the Earth, we choose a sensor with white bands in the range of 10 to 12 micrometers near where the Earth's radiation is at maximum. That is the basis of so-called thermal remote sensing, since we are effectively detecting variations in the Earth's heat output. Although we have shown the curve as a simple continuous line, it thus varies from place to place on the Earth as a result of the property of called emissivity. It is a variation in the emissivity that the thermal remote sensing mission measures and maps. If we extrapolate both the Earth and the solar curves of the previous slide out to the radio wavelengths, we could see that there is a negligible emitted or scattered energy from the Earth's surface at those very long wavelengths. In fact, there is some, and it can be detected with very low spatial resolution instruments. But in general, we assume that the Earth is quite at radio wavelengths. As a result, we can radiate the surface using an artificial energy source, such as a radio transmitter carried on an aircraft or a spacecraft. A receiver on the platform detects scattered radiation, which is then used to create a radio or a microwave map of the Earth's surface. That is the basis of the radar remote sensing. So the key points that is covered in this theory, that is in the theoretical video here, the optical remote sensing system measures the reflected sunlight. We can also image the heat coming from the Earth itself. That is a basis of the thermal imaging. The fire burning on the Earth's surface can also be detected and mapped. Some sensors the image with hundreds of closely spaced wavebands, so-called, so that the fine details in the reflecting spectra can be detected. Those sensors are called as a hyperspectral, as against the multispectral when fewer than about 10 wavebands are used. The water absorption bands are generally avoided with a multispectral sensors. So there are three important messages here. Number one, the imaging can be done with a reflected sunlight. The thermal emissions from the Earth itself or via scattered radio waves or the radar. Secondly, note the difference between the hyperspectral and multispectral imaging. And thirdly, remember the water absorption bands need to be avoided. So in this video of remote sensing tutorials, we've shown you what are we trying to measure from the Earth's surface. So thanks for watching, and please subscribe to our channel and give us a like.